So imagine that we already know that this difference between men and women in relation to their feelings about immigrants is statistically significant, which means that it was not produced by random processes, it was not produced by chance. But we are to some extent confident that this effect is real in the real population. And so what's the next step? What we want to know, the second inferential step, is to try to estimate the extent to which this effect is meaningful, or the strength of the effect of gender in the feeling thermometer about immigrants, for instance. And that's what is called the substantive significance of the relationship between X and Y. Okay? We use the measures of association to try to estimate that level of significance. And we want to select measures of association that have two characteristics. The first one is that they use something that is called the proportional reduction in error. So we want to know the extent to which using the independent variable is useful to predict the dependent variable. And the way that we know that it's useful to predict it is because we want to see the difference between knowing the value of the independent variable in comparison to not knowing it. If knowing the value of the independent variable help us to reduce errors, is because we can predict the dependent variable in a more effective way with the independent variable. Okay, that's what is called the proportional reduction in error. And this proportional reduction in error magnitude ranges from 0 when there is no error reduction and 1 when there is complete error reduction. In other words, 0 when the independent variable doesn't provide any predictive capacity, and 1 when it has the total level or the full capacity of predicting the dependent variable. Okay? Similar to the significant test, we want to see larger values of proportional reduction of error, because that means that the effects of X on Y is more meaningful. Okay, if the reduction of error is very small, the effect of X on Y is very weak. So we want to have very large values of the proportional reduction in error measure. Okay, that's the first thing. The second criterion that we need to keep in mind when we want to select a robust measure of association is that this measure needs to be asymmetric. An asymmetric measures of association considers whether the first variable is the independent variable and the second variable is the dependent variable. So it is sensitive to the side of the relationship that we are proposing, and it's going to give us different values according to which is set as the dependent and independent variables. Okay? A symmetric measure of association, on the contrary, is agnostic about causality, and for that reason it's not very powerful and is not very useful for us. Okay? So the first measure of association that we're going to learn here is lambda. Lambda is used to especially to study the relationship between nominal variables. And let me give you an example. Look at this table, and for instance, if we want to know the extent to which gender predicts the approval of abortion in this sample, so what is the predictive power of gender? So we're going to do the same as we did with the significant test. We're going to talk about the assumptions, we're going to talk about the special notation or the estimation of each measure of association. Later we're going to talk about the interpretation. We're going to mention some of the limitations of these measures, if any. And finally, we're going to talk how to estimate these measures and interpret them in R. Okay? So lambda has a special notation. And the formula of lambda is based on the difference between the values that you obtain when you predict error without the knowledge of the IB, and the values that you obtain when you predict error with knowledge of the IB. Notice that we call prediction error without knowledge of the IB as R, because we are talking about the rows. And what we do here is that we use the distribution of the dependent variable, which is approval of abortion, and we're going to use the mode. In this case, the mode is going to be no, and it's going to be 57.3, right? So when we use the distribution of the dependent variable, or the rows here, the error that we're going to predict is 537, which is yes, okay? And this is called prediction error with knowledge of the independent variable, are called columns, because we're going to use the distribution of the independent variable here, okay? And we're going to do it for each column. So for women, the mode is going to be no, and the error is going to be 302, which is yes, okay? For men, we're going to do the same, and the error predicted is 235. And finally, the total value of the column, or the prediction with knowledge of the independent variable, is 537, which is actually the same value of predicting error without knowledge of the independent variable. And that's a clue of what's going to be the result of this measure. So this is the formula of lambda, and notice that we want C to be very low, because if it is very low, even if it is 0, our lambda is going to be 1. That's what we want, right? So think a little bit about it. So if C is 0, that means that C is a very good. So knowing the value of the independent variable allow us to reduce error. Like we're not gonna obtain errors if C is 0, right? So and for that reason, lambda is gonna be very high. So the predictive capacity of the independent variable is gonna be very high, right? In terms of interpretation, in social sciences, so we usually have low levels of prediction in social sciences, and if lambda is less or equal than 0.1, we say that the independent variable has a weak predictive power. Okay, it has a moderate effect if lambda is in the range higher or greater than 0.1 and smaller than 0.2. Okay, it has a moderately strong predictive capacity if lambda is greater than 0.2 and less than 0.3, and it has a strong predictive capacity if it is greater than 3. Okay, in this case, for example, as I mentioned, lambda is equal to 0, because remember that the value of the column was the same of the value of the rows. Okay, so gender is a very weak predictor of approval of abortion in this case. Okay. Okay, one of the limitations of lambda is that when there is little variation in the dependent variable, such as in this case, in both categories of the independent variable, the dependent variable is going to be approval of abortion. So you don't have, so approval of abortion is the mode for both columns. Lambda is weaker to, or doesn't work very well in that kind of situations. And there are some corrections to these problems. You can use other methods, but I think lambda is still one of the most useful methods for nominal kind of variables. Okay. Now, in terms of how to estimate lambda in R, we're going to use the same dataset, the 2018 CCES dataset, but in this case, we're going to install and charge the package desk tools. The name of this package comes from Descriptive Statistic Tools, and it is an incredible package, supremely useful, and you can explore different functions that you can find here. You can even create a mosaic plot that is very useful to describe your data. So in the replication materials that I'm going to give you, attached to this lecture, I wrote two different functions that are very useful with this package. So explore this package because it's going to be very useful for you guys. Okay. A little bit of background. Imagine that we claim and found evidence that the relationship between the approval of President Trump is statistically significant, or it has a statistically significant effect on the public opinion related to provide Medicare for all Americans. Okay, so we found evidence that that relationship is statistically significant. So what we want to know now is the extent to which a nominal version of that variable, of that X variable, which is disapprove or approve, actually help us to predict a nominal version of the independent variable. In this case is support or oppose Medicare for all Americans in the US. Okay, then we use lambda. So we're going to use a function that is called table that comes from the descriptive tools package, or the desk tools package. And as usual, we're going to use blue to talk about objects such as datasets, or in this case, this table one is going to be an object. And we're going to use here the variables with in green lines, okay? Something that is very important to know here is that our dependent variable is going to be the first variable, and our independent variable is going to be our second term, okay? And that's important to keep in mind, because if you do the opposite, as I said, lambda is going to give you another value, because these measures of association are sensitive to what is the dependent variable and what is the independent variable, okay? Another thing that is important to mention here is, okay, no, that was the first step. So you create the table, and later you put the table, or you write the table in this function, and the function is lambda. And so you use the table that you just created, and you say the direction. This part of the function is critical, direction, because you're telling R use row as my dependent variable. So rows are determined by the values of the dependent variable. Okay, if you write a column or you don't write anything, probably R can estimate something different than what you are expecting. Okay, and the other thing that is interesting to mention here is that the function gives you the confidence intervals. So even these kind of measures of association also have standard error and confidence levels. Okay. Okay, so you run that in R and you find this very simple kind of results. You have the confidence intervals, but more important, you have lambda. And remember that these measures of association go from 0 to 1, and 1 is perfect prediction, and 0.26 is actually a morally strong predictive capacity of these independent variables. So we can claim, or we can conclude that the approval of President Trump is a morally strong predictor of support to provide Medicare for all Americans, which is not surprising, of course, but this is a good example. Okay, so that's lambda. Now let's move to Summers DYX. Summers DYX is a very similar measure of association to lambda, but the difference is that the Summers DYX gives you, or is used with ordinal variables, and the advantage of the ordinal variables in comparison with the nominal variables is that the ordinal variables tell you about the the sign of the effect, or not necessarily, or not only the sign of the effect, but the degree to which one variable affects the other variable. Okay? For instance, in this case, we claim that religious attendance is negatively related to the support of abortion rights. And we have this ordinal independent variable of religious attendance, which goes from frequent, occasional, and infrequent, right? So what we are saying here is that as we move to higher values of, or in this case, to lower values of religious attendance from frequent to infrequent, we might expect, it's crazy this distribution of the table, but we might expect more support to abortion rights. Or the opposite, when we move from lower levels to higher levels of religious attendance, we can expect lower levels of approval of abortion, which is actually our hypothesis. Okay? Okay, so as lambda, Summers dyx has a special notation and a special logic of estimation. Okay, when you have a table, whatever is the table, and when the cases are distributed from the upper left, such as here, to the lower right, such as here, that's what is called a measure, when a relationship is measured as positive, okay? Such as in this case. The crazy thing about this table that I that I copied from Pollock is that for some crazy reason he put frequency first and later occasional and infrequent. And I'm sorry, not frequency, but frequent, occasional, and infrequent. And that's not the best way to do. And I strongly encourage you guys to put first, try to think of the columns and always set the values of the columns or the categories as if they were ordinal to some extent. So put from low levels to high levels. So here it should be infrequent, later occasional, later frequent, or from negative to positive, or from inexistent to existent. Okay? And the same here. First goes the inexistent category and later the existing category. Okay? That's very useful for the analysis, but it's fine. So this is not critical in this moment, but it's going to help you to interpret the results. Okay? And they say, or in the logic of Summers, dyx, this is called a positive relationship. Okay? If it goes in the opposite direction, which is from the lower left to the upper right, this is called a negative relationship. And this is important just because we call, in the notation of Summers, concordant pairs are pairs of observations that are consistent with this positive distribution or this positive relationship. And let me give you an example. And it's simple like this. It's simple like this. You just, if you wanted to estimate this Summers dyx by yourself, which I do not recommend you to do it because it's not very useful. But basically what you want to do here is that you create pairs that go from 7 to 5, 7 to 6, and later would be 5 to 6. And you just multiply those pairs and sum the value of those pairs, as I have here. Okay? As I have here. That's the concordant pairs. There are discordant pairs. There are pairs of observations that are consistent with a negative relationship. So it's basically the opposite. So you go from 3 and you multiply 3 for 5 and sum that multiplication with the sum of 3 and 4, and later it would be 5 and 4 and so on and so forth. Okay? So you have concordant pairs, you have discordant pairs, and you have also dyad pairs. And dyad pairs are observations that are have different values of the independent variable, but have the same value of the dependent variable. And the problem here is that you expect that if they have different values of the independent variable, they should have different values of the dependent variable, right? That's what we expect with this kind of hypothesis. But this is an example of a tied pair. For instance, frequent and no, occasional no, and infrequent and no. Okay? And it's similar to the same. You create pairs, multiply, and later sum. And you use in the formula, thus you use the values of the concordant pairs or the sum of all concordant pairs, all discordant pairs, and you subtract the discordant pairs to the concordant pairs, and you divide it by the sum of concordant, discordant, and tied pairs. Okay? Okay, so if the number of concordant pairs is higher than the number of the discordant pairs, and the tied pairs are rare in this table, then the dyx is close to 1. So it's going to be strong and it's going to be positive. Okay? If concordant pairs, or there are less concordant pairs than discordant pairs, and again, the tied pairs are rare, you're going to have the opposite. So you're going to have a very strong situation, or a situation in which the independent variable has a strong predictive capacity, but the relationship is going to be negative. Okay? And when the concordant and discordant pairs are roughly equal and there are too many tied pairs, the independent variable is going to have a very weak predictive capacity. So dyx is going to be close to 0. Okay? So again, what we want to have is a very strong predictive capacity, and hopefully in the sign of the effect that we expected. Okay? The interpretation is the same, but interpreted as the absolute value of, in this case, is Summers dyx. Okay? In this example, the Summers dyx has a value of 0.2. That is a moderate effect. So we can say that religious attendance is a moderate predictor of the approval of abortion. Okay? Okay. To estimate Summers dyx in R is very similar to what we did in Lambda. We're going to use here the same data set and the same package. You just create an ordinal version of the support to Trump. And it is important to filter and exclude the cases that are called have the category 5, which means not sure, because that category is not meaningful, right? And you order in whatever the way you want to do it. As I said, I really want to do it from negative to positive feelings. For instance, in this case, strongly disapprove, somewhat disapprove, somewhat approve, and strongly approve. That's the way I prefer to do it, always from negative to positive. But I don't know why, in some cases, some data sets have the opposite kind of order. I don't know why. Okay, I created here also a nominal version of support to the policy of interest, which is provide Medicare for all Americans. Okay, so we want to do the same as in Lambda, but we want to use, in this case, the ordinal version of support to Trump. That's the only thing that we want to do. Okay? So, as I said, my strong advice, and I'm going to repeat it because it's very important, is that it is a good idea to set your columns and rows in such a way that the categories of the independent and dependent variable goes from low to high, from negative to positive, or from inexistent to existent. Okay, because that's very useful for the analysis. And okay, so we create a table, and just I want you to remember that the first variable in this function is going to be the dependent variable, and the second variable is going to be your independent variable. Okay, the only function that you need to learn here is table, which comes from desk tools. And later you use the function Summers delta, okay? And you use your table that you just created, and similar to the case of Lambda, you use this part of the instruction is very important. Direction is row, because you are telling R that the dependent variables are determine the rows of your table. Okay, and that's all. You're gonna have a very similar result. In this case, as we expected, the effect of ordinal version of support of Trump is going to have a negative effect on the support of provide Medicare for all Americans. This is a very interesting result, no? So it's or no, but interesting, no? It's a very, I don't know. I like the way that they'll like Summers DYX tells you not only how strong is that relationship, but also the sign of the effect. That's very cool. So you have a negative effect here, as you expected, actually. So you can conclude that this is a very strong negative predictor of the policy of interest. Okay? And you also have your confidence intervals here.